let's talk about span for V1, V2, Vn in V. We define the span of V1, V2, Vn. And in many cases, it's helpful to preserve the ordering, so I'm going to put this as a list. I explained that the difference between a curly brace and a parenthesis is that curly brace is a set, and in a set, you don't have ordering. V1, V2 is same as V2, V1. Here, in a list, you do have ordering, and V1, V2 is not the same as V2, V1. And also another important difference is in a list, you can have identical elements. In a set, if you have V1, V1, that's same as just V1. Identical elements are counted just once in a set, whereas in a list, even if these two are the same, if it's a list, you do have to preserve the number of items. So in many ways, it's more advantageous to use a list over a set when you're trying to describe the span and linear independence, and we're going to go towards describing what a basis is, and so we'll frequently make use of the list instead of sets. Okay, so what is this span of V1 through Vn is a set of A1 V1 plus A2 V2 plus AN Vn, where A1, A2, AN, all of these coefficients are from the base field. So if V is a vector space over some field F, then this is what the span is. As noted in the first lecture, that when we say vector space over F, F is usually R or C. Okay? We don't really consider other special cases because those are too hard. So I'm just writing F for what could be written as R or C. Okay, so that's what a span is, and additionally, we define span of an empty list. So I said I'm using list, but this is more like a set. But yeah. So an empty list is same as empty set, and in that case, by convention, we just define it to be the trivial vector space. I mean, if none of V1 through Vn's are present, you can't get this result from this definition alone, so you just take that as a separate case and define it like this. This way of defining things simplifies a lot of the other statements. That's why we have this. Or else, every time we define something, we have to take this as a special case, or say it's a non-empty list or something. We don't want to talk about those. So that's often the convenient convention to use. All right, so what can we say? The first theorem, theorem 2.7, says that span V1 through Vn is the smallest subspace containing V1 through Vn. Okay. Let's prove this. To show that something is a subspace, what do you show first?
0.
Hmm?
The existence of 0.
Yeah, you have to show that span contains 0. Now, when does this kind of element become 0? Every AI would be 0, right? If you have 0 V1 plus 0 V2. Okay, so you say 0 is equal to 0 times V1 plus 0 times V2 plus da da da, 0 Vn. And of course, because it looks like exactly like this with A1 through AN being 0, this is indeed in the span of V1, Vn. Yeah, I'm getting tired of writing 2 parentheses and then V1, V2, so it's like, forgive me if I write in a simpler way. All right, so that's part A. What's the next thing I have to show? It's closed under addition. So if U, W are in the span of V1 through Vn, then we have to show that U plus W is in span of V1 through Vn. Okay? How do we show that? We have to think about what it means to be in the span. Well, that means U must be A1, V1, da da da, AN, Vn, and W must be B1, V1, da da da, Vn, Vn. I can't use A1. Repeat. I already used A1 here, so I have to use something else. I'm using B1. But because we're using the same V1 through Vn, the V1 through Vn shouldn't be changed, right? Only the coefficient should be changed. Then, what is U plus W? Well, U plus W is then A1 plus B1 times V1 plus da 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 AN plus Bn times Vn, and of course this is indeed in the span because it has the structure of some scalar times V1, some scalar times V2, and then some scalar times Vn. Right? Okay, next, what do we have to show?
Closed under multiplication. First scalar multiplication.
Yeah, so if C is in F and U is in span, then we have to show that this set is closed under scalar multiplication. In other words, if I do C times U, it should still be inside the span. Okay, so it has to be C times U has to be in the span. And the proof of that would be, oh, that's right, because here. Because U is equal to A1 V1 plus AN Vn, and C times U would be CA1 V1 da 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 plus CAN Vn. And if you multiply C to this, you can distribute the C to every one of these. And of course, this is again in the span of V1 through Vn, because if you look at this, this is in F, right? Maybe I should write it red. Let me do this again. C1, A1. Since C1 is in F and A1 is in F, not C1, A1. Since C is in F and A1 is in F, this is indeed in F. So is this one. Every coefficient you see belong to F, and therefore it does meet this criteria. All the coefficients are in F, and those are multiplied to each of the vectors V1 through Vn. Therefore, that's in the span. Okay, so what does this show? ABC shows that.
It's a subspace.
Yeah, thus span V1 through Vn is a subspace. Okay. What remains to be shown is that it has to be it's the smallest subspace containing V1 through Vn. Okay, so since V1 is equal to 1 times V1 plus 0 times V2, 0 times Vn, and it's the definition of the fields require that every field has to have a 0 element and a 1 element 1. So even if F is kept in general, I always have a 1 and 0 in the field, okay? So I can put a 1 here and then 0 for every one of them, and of course if you calculate this, this is indeed the same as V1. But if I write like this, this shows that span of V1 through Vn contains V1. Okay? And you can do the same thing for V2. V2 is 0 times V1 plus 1 times V2 plus 0 times V3, and then keep going with zeros. Again, this is in span. Sorry, I'm too lazy to write this down again, but hopefully that makes sense, okay? So you continue this on, and that shows that Vn is also in the span. So we've so far shown that this is a subspace, and it's a subspace that contains all the V1 through Vn. Okay? But to show that it's the smallest subspace containing V1 through Vn, it's let's just say hypothetically that W is another subspace that contains V1 through Vn. Then we have to show that span is in there. Okay, so to show that span V1 through Vn is the smallest subspace, we have to show that any subspace W that contains V1 through Vn must satisfy span of V1 through Vn is a subset of W. Okay. So I'm just rephrasing this statement. Being the smallest subspace means that any other subspace must be bigger. Now, what does it mean for one set to be bigger than the other? Well, if it contains the other, then it's bigger, right? So that's how I'm rephrasing this. Now, so proof of above. This statement, how do you do that? Well, for any A1 V1 plus da 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 AN Vn in the span. See, how do you show that one set is inside the other? You just pick any random element from one set and show that that element can be found in the other one as well. Yeah. That's how you show a set inclusion, right? A1 V1 is in W because V1 is in W. That's one of the conditions, right? Yeah. And being a subspace means that W is closed under scalar multiplication. Okay. And in the same way, we can say A2V2, A3V3, all the way until ANVN is in W. Okay? And now that you have all of these inside W, then A1V1 plus da 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 ANVN is in W. Now, what kind of property should I be using? Because W is closed under vector addition, right? Yeah. W is closed under, I'll just write down plus, okay? And that proves it because I chose any random element in span. They all look like this. And I was able to show that this actually belongs to W. So if you pick anything from here, it belongs here. So this is a subset of that one. That shows this smallest claim, right? Let me put an example problem. So describe span of 1, negative 1, 0, and then 2, 1, 3 as a hyperplane in R3. Okay, so we're thinking of R3 as a vector space, and in there, if I span these two vectors, if you have two vectors, although we haven't talked about dimension in this part, what kind of geometric object do we get in R3? We get a plane, right? And any plane in R3 is described by a single equation. And the question is, can you find that single equation? So let's try to do that. So solution. What's in here? What's in the span? What do we collect?
Linear combination.
Yeah, so we just have to do a times 1, negative 1, 0, plus b times 2, 1, 3. So collecting all of these is what the span is. Let's investigate further what this does. This means this portion is a comma negative a comma 0 plus 2b comma b comma 3b, and that gives you a plus 2b, negative a plus b, and 3b. And we really have x equals to a plus 2b, y equals to negative a plus b, and then z equals to 3b. But then, what are we trying to do here? We're trying to say that something times x plus something times y plus something times z equals 0. That's what a hyperplane means, right? So let's pick the numbers. Unfortunately, I want to use ABC here, and I already used ABC. So a better approach would be to use S and T. That's the usual one. Since I already use S and A and B, let's just use SRT. So we're going to say SRT. And let's plug in these things and see what we have. We have S times A plus 2B plus R times negative A plus B plus T times 3B equals 0. And then if we collect all the A's, it's S minus R times A. And then if I collect all the B's, it's 2S plus R plus 3T. Is that right? Yeah, I think it's right. Okay. Equals, sorry, B equals 0. Now, what I need is that this has to be true for any A and any B, right? See, this generates all kinds of points, but I want a single equation that would be satisfied for any A and B, right? So if you plug in 1, 0, it gives you 1 point in this hyperplane, right? If you plug in 0, 1, you get another point. You can plug in 1, 1, 1, 2, 3, 1, you name it. You can put anything for A and B, you get a point in here. That has to satisfy this equation, right? So this has to be 0 for any A and B. That means this has to be 0 and that has to be 0. Okay? So we see that S minus R has to be 0. 2S plus R plus 3T has to be 0. And you can see that this is a underdetermined equation, right? You have 3 unknowns, S, R, and T, and you have just 2 equations, which means there's like 1 degree of freedom. The first one says S equals to R, and because you have 1 degree of freedom, you can set one of them to any value you want, as long as you don't put a 0. If you put 0, then everything else becomes 0, so it's not good. So let's pick 1. Let's say R is 1. If R is 1, then S has to be 1 because of this. And then when you plug in 1 and 1 here, what do you get for t? 3 plus 3t equals to 0. So you get t as negative 1, right? Okay. So it looks like it should be 1, 1, negative z. So I think the answer is that span of 1, negative 1, 0 and 2, 1, 3 is equal to set of all points x, y, and z where x plus y minus z is equal to 0. Let's see if this is true. Does this satisfy this? 1, negative 1, 0. 1, negative 1, 0. Does this satisfy this? Yeah, right? How about this one? 2, 1, 3. 2, 1, 3. This satisfies this as well, right?
Yes.
Okay. So since these two satisfy this, any linear combination of this will still satisfy this as well, because we know that this is a vector space, right? We know that anything that looks like ax plus by plus cz equal to 0, that's a subspace of R3. And that, because it's a vector space, if you have two vectors that's in here, then any linear combination of that should be in here as well, because of the theorem that we just proved, which is that if you have a span and a vector subspace that contains each of these vectors, then we know that this is a subspace of this. Okay? So just by plugging these two into here, we already know from the previous theorem that this is a subset of this one. How do you know they're equal? Well, that requires a little bit more computation. Like if you take anything that looks like this, then anything that satisfies this equation will be x comma y comma x plus y. Because if you solve this for z, z has to be x plus y, right? So I know that anything that looks like, anything that satisfies this must look like this, and then you want to rewrite this as x times, so it should be 1/3 x plus y times 213. That's because 1/3 times 3 gives you 1, and 1 times x plus y gives you x plus y. And this is 0, so it has to be this guy. And then 2/3, so it'll be 2/3 x, 1/3 x minus y times 1, negative 1, and 0. So if you do 2/3 x plus y plus 1/3 x minus y, no? That should work. X gives you 1/3. What am I missing here? I'm forced to say that x plus y times 1/3 times 3 gives you x plus y. 2 1/3 x. I'm stuck. What's going on? 2 2, 1, 3. Anything that looks like x, y, z has to be x plus y, that's true. And for this coordinate to be x plus y, we better have, since this is 3, we better have x plus y. Oh, sorry. Minus 2y. Okay, then everything works out. Okay. So if you have 1/3 x minus 2y and 1/3 x plus y and multiply by 2, if you simplify this, you'll get exactly this, okay? So that shows that anything in here can be represented as in the span. So yeah, that takes a bit of work. Yeah, but the whole purpose of this, well, okay. So I wrote it like this, but later on, when we have the concept of dimension, then it's a lot easier. We can just say that this will have a dimension 2, and since this is also dimension 2, they have to be equal. So that's the way we're going to proceed later. If we learn something more about vector spaces, but if you only have span, then you have to manually find this result, which is a bit more challenging. But rather than being scared about having to do this, what I want you to have a feel for is, what is a span? Span is taking linear combinations and collecting all of them, okay? And if you do that, you get a vector space. I wanted you to have that feel, right? Okay, definition, finite dimensional. Let's talk about finite dimensional. You may have noticed that we haven't defined what a dimension is yet. Okay? Although we intuitively know what a dimension is from our experience in review of the Rn and its subspaces. When you're doing the abstract vector spaces, think about what we've defined so far. We defined what a vector space was, what a vector space is, and we defined what a subspace is, and we defined the vector sum of vector subspaces, and we also defined what a direct sum is. Now we're defining what a span is. That's all we have done so far. We covered very little. Okay? When you have to prove every detail of something, you end up going really slow. But the payoff is that because you're doing abstract work, you can apply to many more wider circumstances than just using an Rn. Okay? I guess the biggest difference between math and physics, both very hard sciences, they use logic for everything, is that for math, we do definition and proofs. Okay? We think about what's the best definition to hold the widest applicability, and once you come up with a good definition, now you start proving theorems. That's how math is taught and learned, and that's how you advance math. On the other hand, physics, what they do is they do experiments and they come up with hypotheses, and then when it comes to explaining something, they don't really prove anything. Rather, what they do is they make analogy. You say, oh, such and such things happen because of this and this. And when they try to come up with an analogy, often what they do is they come up with something called a toy model. So if a physicist is trying to do linear algebra, the way they're going to do it is they're not going to do any of these, and they'll just happily do Rn, that's it. And maybe do some Cn, because Cn has some other properties. So complex numbers have some additional things that you can't do in Rn. So they might do some Cn. But once they're done with Cn, they wouldn't do any abstraction. They're just going to say, hey, here's a model, and in this model, like forces can be thought as vectors. What are vectors? Think of this, Rn, and you put 3 real numbers, and this is like a vector. And they talk about something that happens in Rn and say, by analogy, this will also happen in mechanics. That's the way physics proceed. Okay. Now, which is better? Well, you can't really say. Sometimes the hard proof way would be able to shine on things that analogies can't go, okay, it can't reach. And sometimes analogies can bring in new insights that hard proof sometimes cannot find. Right? So they're both pretty important approaches, but we're in a math class, so we're really trying to define everything and we want to show everything. And I just wanted to mention that we haven't talked about what dimension is, but we're just going to define what a finite dimensional space is. Okay, so finite dimensional. If V is spanned by finite number of vectors v1 through vn, then we say V is finite dimensional. There's something that you might misunderstand. You might think, oh, okay, so you have n different vectors spanning this, so this V must be n dimensional, but that's not true. You might have the same V repeated. There's nothing stopping that. So in actuality, which we're going to prove later, is that if V is spanned by V1 through Vn, then the dimension of V is less or equal to n. It's not equal to n, but it's less or equal to n. Okay, but because this is finite number, the dimension of this must be finite as well. So kind of makes sense, right? Yeah. So it's always good to have a concrete example in your head when you see abstract definitions, because you want to take that definition and apply it to your concrete example and see if it makes sense or not. Okay. All right. So now let's talk about this. We have to show that PMF is finite dimensional. Earlier today, I explained what P3F is. So what is this thing again? It's a space of, or it's a set of polynomials. Okay, polynomials. I'm skipping the part that shows that this is indeed a vector space. We're just going to say it should be somewhere in the book. Okay, so let's say this is already a vector space, and we want to show that this is finite dimensional. Well, what's in here? Any function in here is f of x is am x to the m plus am minus 1 x to the m minus 1 all the way up till a1 x plus a0. But this already looks like a span, right? Especially if you rewrite this as a0 times 1, then you see that this is inside span of xm, xm minus 1, all the way up till x1. And since this is finite number of vectors, you've shown that this is finite dimension. Done. On the other hand, P of f is infinite dimensional. This is a space of all polynomials with coefficient in f. Okay? And we're trying to show that this is infinite dimensional. How do you show that? Well, a lot of things that's hard to prove often resort to like proof by contradiction. You want to start by suppose not. Okay, so suppose here proof. Suppose not. In other words, that P of f is equal to span of f1, f2, all the way to fn. I should really say fn parenthesis x, but I'll just write it like that. So when I say f1, I really mean f1 of x, which is a polynomial, right? So suppose that's my pf. Then let m be the maximum degree of f1 through fn. See, anytime you write something like this could be degree 3 polynomial, this could be degree 5 or degree 10. Any polynomial has a degree, right? This space is not a space of power series. That's actually a slightly different matter. It's hard to argue. Power series, what's a power series? Power series have infinite degree, right? Power series is something like 1 plus x squared, xn, keep going. That has infinite degree, okay? So if you work with this space, that's hard to show that it's infinite dimensional. Well, we can actually show that this is infinite dimensional because these are going to contain anything in here, and this is infinite dimensional. But to use that kind of argument, you need to know some other theorems that we're proving later. Okay, but that's just for the future. What I'm trying to say is that these are polynomials. Polynomials have finite degree. It could be degree 100, it could be degree a million. We don't care, it's some finite degree. Right? Okay. So let m be the maximum degree of these, because every degree is a number. You have n different numbers, you always can find the maximum number, right? Okay. So such an m should exist. Then if you take the linear combination, sorry, 2 is also at most degree m, because the highest degree of any polynomial here is m. You can't express anything that's higher than degree m. Okay? What this means x to the m plus 1 is not in the span of f1 through fn, right? While x to the m plus 1 is clearly polynomial, so it does belong to P of f, which is a contradiction. Okay? Contradiction I'll use this notation, contradiction. Have you seen other notation for contradiction? I've seen something like another notation for contradiction. This is like thunder. Yeah. Like serious problems happen. That's contradiction. I like this notation because it's like two things going against each other. You know, in the ancient Chinese world, there's a story where a person was selling weapons, and he took a spear and said, "This spear is so strong and it can penetrate any kind of shield." Okay, and then after trying to show the spear, then he took another shield and said, "This shield is so strong, nothing can penetrate this shield." And then someone in the crowd said, if those are both true, what's going to happen if you try to pierce the shield with the spear, with your spear? And the person couldn't reply. So that's that's the Chinese word for contradiction. Yeah. You guys probably know better. Who can speak Chinese here? Do you know Mosun? I don't know what that is in Chinese. I'm Korean, by the way, so I don't. We just say Mosun, and it comes from spear and shield. That's the Chinese character. Don't you use that as well? No.
I'm not that good at Chinese.
Oh, okay, yeah. All right. So that's contradiction. It's a contradiction because we said two things are equal, but I found something that's in the left. That's an element of the left side, whereas it's not an element of the right side. And because we found a contradiction, what must be true? It must be that this is infinite dimensional. Okay.